Hi, please tell the good morning. Tell those who are in the Connect link to join YouTube channel because the Connect seemed to have a problem. I wasn't able to use the speaker, so he couldn't hear me. He told me allowed uh, joining through only through earpiece, which means that the audio wasn't working. So please tell your colleagues to join. Okay, I can see we have 48. Yeah, as we set up, we're going to have some problem dealing with the attendance, but hopefully we find a way to deal with that. Okay, so the last time 49. So I don't know. I think we should be more than this. 407. Okay. I can see there are people on the other link, still on the other link. Please tell them to join YouTube live. Had we finished with this? I think we had finished with that. Let's see. So please, class attendance is still mandatory. I can see only 128. Yet the class should have over 300 students. Okay, I'm not sure where we left last time, but so this two. So please note that okay, good morning and welcome. Note that we will need to make up for the lost time. Okay. I think we left somewhere. Defining what an engineer is. Okay, I think somewhere here. Somewhere there. Okay. So I can see some other people on the other link. So please tell them to join here. Okay, very well. Can you hear me? Please, someone type. Can you hear me and see my notes on the screen? Classroom. Someone type on the chat so that I can. Okay, Ron says they can hear me. Okay, very well. Um, okay, so we move on from where we left last time. We were defining what an engineer is. An engineer is defined as a person qualified in engineering, a person who maintains or controls an engine or machine or a skillful contriver. And skillful contriver may mean many things. Uh, a person who can design and build, and in fact, that's all engineers are known for. Um, one who skillfully arrange for things to happen. So um, we imagine, scientists imagine things, engineers help to make those things a reality. Okay, so we can skillfully make things appear magically, more like creators. You imagine, but then that's not the same as actually um, actualizing the imagined idea. And then C, one who can modify an organism by manipulating its genetic material. You know about GMO, okay? The origin of the word engineer is from a Latin word, ingenium. If you see engineers from mostly Europe, Germany, they use the shorthand ing instead of in this. I think in Kenya we use. In Kenya, you'll often see people using engineer, or in some jurisdictions they use eng with an R. In Germany, you see they use, from Germany mostly I've seen, they use ing. Okay? Engineering has existed since ancient times as humans devised fundamental inventions such as pulley, lever, and wheel. Each of these inventions is consistent with modern definition of engineering, exploiting basic mechanical properties to develop useful tools and objects, according to the author Barry in 2005. The engineering itself has much more recent etymology, deriving from the word engineer, which itself dates back to 1325. Um, when an engineer literally meant a person who operates the engine. I think that's something we have talked about. I realized at this part we had gone through it. I can see the attendance is still not very good. Please this class should have around 300 students or 250 thereabout. I'm only seeing 147. Please let your colleagues know that attending class is important unless people are sharing devices. So literally means a person who operates the engine, originally referred to as constructor of military engines. In this context now obsolete, an engine referred to a military machine. Okay? mechanical contraption used in war, for example, catapults. Notably, exceptions of the obsolete usage which have survived to the present day are military engineering corps. So in your study of engineering, you'll see a lot of references made to some standards from the U.S. Army of Corps. The word engine itself is even older origin of an older origin, ultimately defined from Latin ingenium, I already said that, and meaning innate quality, especially mental power, hence clever invention. So later, as the design of civilian structures such as bridges and buildings matured as technical discipline, the term civil. So this is kind of engineering started from rudimentary terms. So people who operated engines remember the revolution, the industrial revolution, the invention of the steam engine upgrade. So this needed some form. So the term engineer was used for people who could make uh, the engine, such like stuff. But also in the military, because when people are fighting, you usually need some fortification, some kind of service. Okay. But now, as the world continued, people developed, population increased, we needed things like, because engineering was traditionally associated with the military, but so out of the military, we talk about the civilian, people who have no army training. They need bridges, they need buildings, they need good water as supply and so on. So then the development of civil engineering, meaning that now it is divorced from the uh, um, divorced basically from the military context. So is civil engineering entered the lexicon as a way to distinguish between those specializing in construction of such non-military projects and those involved in the older discipline. So it was initially in the military, but now because people who civilian people, just like the name suggests, people who have no military training still need things like bridges, buildings, they need good water supply and so on. So then this is how the civil engineering began. So some demonstration of the Egyptian pyramids, some old, um, Roman water-powered crane bearing design. So just giving you an idea of the um, transformation of the engineering concept over the years. So pharaohs of Alexandria, the pyramids of Egypt, hanging gardens of Babylon, Acropolis. So there is a lot of debate about who made up the pyramids, like exactly um, how did the pyramids come to be. Okay, so just an exemplification of old structures that exemplify engineering. So hanging gardens of Babylon. So you can type these things on Google and then see what it is about them. Hanging Gardens of Babylon, Acropolis, Parthenon in Greece. So these are some iconic engineering marvels in the traditional sense. Romans, aqueducts by Appia, Colosseum, Teoti, okay, this word, Teotihuacan cities, the pyramids of Mayan, Inca, Aztec empires, of course, the Great Wall of China. Some of this you can see live on Google, the Great Wall of China, Brihadeshwara Temple. So you wonder. The wall is not very tall anyway, but because of the, you know, the sheer length of the wall, and they used very rudimentary tool. So you still wonder how the resilience with which, because it's a very long um, length of wall, and and just made through rudimentary means in a very uh, old time. So just to put this in context, I think the Kenyan-Somali border is about 1,000, maybe 1,000 at the very maximum, or around there. Now, if you do an estimate how much resources it will take to put um, to fence that stretch. You see, remember also the story of Trump putting a wall between Mexico. That did not go very well. And if you look at the sheer amount of resources that was at stake, okay? So if you compare this with the Great Wall of China, then you can see why, and in a very um, um, traditional, in a very old age, then you can see why it's a marvel. Then we have Brihadeshwara Temple of Thanjavur and the tombs of India, among many others, stand as testament to ingenuity and skill of ancient civil and military engineers. So basically, what he is saying is that the skill, the ingenuity started um, traditionally without. So this started some old or ancient roots. The earliest civil engineer known by the name Imhotep as one of the officials of the pharaoh Djoser, he probably designed and supervised construction of the pyramids of Djoser, the step pyramid at Saqqara in Egypt. He may also have been responsible for the first known use of columns in architecture. Ancient Greece developed machines in both the civilian and military domains. The Antikythera mechanism, the first known mechanical computer, and the mechanical inventions of Archimedes are examples of mechanical engineering. Some of the Archimedes' inventions, as well as Antikythera mechanism, required sophisticated knowledge of differential gearing or epicyclic gearing, two key principles in machine theory that helped design the gear strengths of the Industrial Revolution and are still widely used today in diverse fields such as robotics, automotive engineering, and so on. So, from these very rudimentary, um, old days, very rudimentary tools, we have been able to develop, and today, based on that, we have advanced them to use them in robotics and automotive engineering and so on. Chinese, Greek, and Roman armies employed complex military machines, and inventions such as artillery was developed by Greeks around 4th century. Trireme, the ballista and catapult. In the Middle Ages, the trebuchet was developed. So, just to tell you the history of engineering, and also to see the marvel of engineering from Africa, the pyramid. So, that Africa also has contributed to uh, um, the revolution, as it were, you know, engineering revolution, as it were. Then we got into the Renaissance era. The first electrical engineer is considered to be William Gilbert with his 1600 publication, De Magnete, who is the originator of the term electricity. The first steam engine was built in 1698 by mechanical engineer Thomas Savery. The development of this device gave rise to the Industrial Revolution in the coming decades, allowing for the beginning of mass production. With the rise of engineering as a profession in the 18th century, the term became more narrowly applied to fields in which mathematics and science were applied to these ends. Similarly, in addition to military and civil engineering, the fields then known as mechanic arts became incorporated into engineering. So they having looked at the the history of engineering had developed through the olden ages using rudimentary tools and so on. Now, the modern era, we are able to see what is happening, the planets. Just recently, you are able to see the, what is it? The moon, the orange, the blood moon, so to speak. I don't know how many of you are able to see. Um, Although that did not require any uh, specialized equipment, but the point is we can easily explain why that happens. So we actually even predict, and we knew that it was going to happen. In the olden days, that could happen, and people would start to speculate and say maybe other people would say maybe the world is coming to an end. Speculation. Some people would associate it with a miracle, or religious beliefs and so on. But now we can explain and predict, and that time you are told between this time and this time can go out, and you know and you'll see the bloodshot moon. We can send people to spaces, okay. We can literally within a few hours traverse continents. Remember the Rao 101 from India, I think it's about 8 hours. But in short, to get from Africa to Asia, you need 4 hours, isn't it? 4 hours. I remember flying from Nairobi to Qatar is 4 hours thereabout. That's you're traversing continents in a matter of hours. Now, in 4 hours, I'm sure I would, if in a car, you hardly, unless you're driving very fast, and in which case you'll be arrested several times over the road. In 4 hours, maybe you reach Eldoret from Nairobi, but that means you're doing crazy speeds. Okay, so you can see. So that's then we have, you know, at the station, what do you call this? The International Space Station. We have satellites, we can monitor what is going on in our planets. Okay, then electrical engineering. So these are branches of engineering. Electrical engineering traces its origins in the experiments of Alessandro Volta. So Volta, from the name, and you can see, guess that is the person from whom we named a Volts. The experiment of Michael Faraday, okay. George Ohm, Ohm's about resistance, Faraday, the Faraday's law, and so on. Other so electrical engineers will hear this many times, but I'm sure even the rest of you, you've studied physics, so you've heard about this. Then electric motor, the work of James Clarkson Maxwell law, Heinrich Hertz about waves, and so on, and pulses. In the 19th century gave rise to the field of electronics. The latter invention of vacuum tube and transistor further accelerated the development of electronics to such an extent that electrical and electronics engineers currently outnumber their other colleagues of any other specialty. So apparently, electrical engineers outnumber uh, the rest of us, the other chemical or civil, just because of the revolutions that have happened in this field. So electrical engineering circuit board, wind energy design. So just showing you. So this is in the domain of electrical engineering. But wind can be used power, the rotating mechanism and so on. So if it's generating, for example, okay, the purpose is to generate a power. So that's also a domain of electrical engineers. But I'd have to point out that this is a shared area where this would involve electrical engineers, fine, for the generation of electricity and so on. But also mechanical engineers, the rotating parts will need some mechanical engineering, but also civil engineers so that the stability, we know the motion and so on. So this is uh, an area where it's not only a domain of electrical engineers. So the invention of Thomas Savary and Scottish engineer James Watt, we power is in terms of watts, gave rise to modern mechanical engineering. The math development. So you can see now from electrical engineering, we slowly move to mechanical engineering. During the Industrial Revolution, led to the rapid growth of mechanical engineering both in its birthplace, Britain, and abroad. Then chemical engineering, like its counterpart, mechanical engineering, developed in 19th century during the Industrial Revolution. Um, Industrial Revolution scale, manufacturing demanded new materials and new processes, and by 1880 the need for large-scale production of chemicals was such that a new industry was created, dedicated to the development and large-scale manufacturing of chemicals in its new industrial plants. The role of chemical engineer was to design was the design of these chemical plants and the process. So you remember Fritz Haber process. There's a process of producing ammonia, which I'm sure you studied in chemistry, called the Haber process. And since you went to Form 4 recently, probably remember, and maybe you're still pursuing a course in chemistry. So the Haber process, the process of producing ammonia. However, this can be this is initially meant to be a process to produce fertilizer, and fertilizer so there are two advantages here. One, we have no two prong. I'm saying points here that we increase the production of fertilizer such that we can produce more food and then population increase positively. But remember, this has also been used as a weapon. Remember, what is this? This German guy, um, this dictator, German dictator, used the gas from this process to kill uh, mm, about 6 million Jews. It's called the Holocaust, isn't it? This guy, the name escapes me. This German dictator, maybe you remember. Then Madame Curie was able to um, discover were able to discover radioactivity. Okay, so radioactivity poisoned them, and they died as a result of what uh, they discovered. Okay, um, so that's chemical engineering. Then aeronautical engineering deals with aircraft design, while aerospace engineering is a more modern term that expands the rich envelope of discipline by including spacecraft. Okay, so aeronautical engineering was only about aircrafts, but now we can send people to space. So to expand the field to also include um, spacecrafts, then we need aerospace engineering. You can see Elon Musk trying to test many things to space, so probably he is working in tandem with aerospace engineers. Its origins can be tracked back to the aviation pioneers around the turn of the century from 19th century to the 20th, although the work of Sir George Cayley has recently been dated as being from the last decade of the 18th century. Early knowledge of aeronautical engineering was largely empirical, with some concepts and skills imported from other branches of engineering. The first PhD in engineering, technically applied science and engineering, awarded in the United States went to Willard Gibbs at Yale University in 1863. It was also the second PhD awarded in science in the US, only a decade after the successful flight by the Wright brothers. So we know that the Wright brothers are the first are the people who discovered flying or aeroplanes, as it were. Now, even if they are aeroplanes were basically very rudimentary, made of wood, and some very rudimentary technology. We credit them because out of that idea, people realize you can fly and, of course, have uh, advanced. But remember, Wright brothers were just bicycle, you know. So you need to also, this one should teach you how to be first innovative, but imagine. In life there are people, or sometimes you might have a dream or a bigger idea than what people can ordinarily fathom or think of. Then they'll discourage you and tell you, because you could imagine just a bicycle, a person making bicycle in the village there, and they tell you that they have an idea or a dream of making an aeroplane. You would laugh at them. I mean, typically this is the human reaction. But it also means that if you put your brain or your mind to something, then doesn't matter and genuinely believe that you can do it, then you do it. And you'd see, sometimes I get disappointed with the learned or the people who've gone to school. I'm sure you've seen many on the streets saying they're showing their certificates and say I graduated from this place, but there are no jobs. Sometimes it's a lack of innovation or the self-drive to create something or to make something. Okay, never mind that probably there are a lot of things that are lacking. For example, a good support system, you know, to help you. But I'm sure you've seen some people. I'm sure the other time we saw, was it a bicycle making or a person making tuk-tuk or something, trying really to make a chopper that is flying, okay? And someone, I think somewhere, it was airborne for just a minute. And you see now, if this person were to be encouraged and maybe partner with people who are knowledgeable, then they are able to, from this we get invention. Like I've said, sometimes if we don't get a lot of support, there was the other invention in Kenya. I had, I don't know, I did not see it. Though I just hear we had a Nyayoka. Those are things that if we got a good support, we can make sure they're working. Even basically, if for example, say you want to um, um, make an aeroplane, okay? Um, they are basically, of course, because of safety, the government will also come in because you need to be safe yourself, but also take care of other rule, safety. But sometimes I feel like the government here, sometimes their motivation is more of to make money rather than and then confine the space. So imagine you're an inventor, you're struggling, you don't have the finances, and then out of this squeezing yourself, then you need, a lot of license, a lot of time. So no, now it makes your space of being creative and the freedom to use your brain and try out many things limited. Okay, so that's the point. But I'm encouraging you to go out there and imagine and put your heart to it, and you'll be able to achieve. These were just by makers, and I've been able to revolutionize the ideas. Have revolutionized you know, the industry, the flight industry. There was an extensive development of aeronautical engineering through development of military. So from there, after the Wright brothers, then of course traditionally, there was World War One, World War Two, people competing for resources and so on, and the military, I mean the aircraft was a plus to that kind of engagement. Meanwhile, research to provide fundamental background science continued by combining theoretical physics with experiments. In 1990, the rise of computer technology. The first search engine was built by computer engineer Alan Turing. So main branches of engineering. So we started with civil, then electrical, mechanical, chemical. Now we're talking about aeronautical or aerospace. So we branches. We have aeronautical, which deals with aircraft, but aerospace is more modern to term spacecraft. Then chemical engineering, the application of physics, chemistry, and engineering. So please understand the differences between engineering and science. Science, we have the scientific understanding. Engineering, you want to imagine, actualize what the theory from science is doing. So, for example, the science of let's see, the science of um, the science of aircraft flying. You have to make it streamline, isn't it? Streamline, and we know uh, from Bernoulli, okay. But remember, this has a constant. The aeroplane will have a constant speed, okay. But this distance is much longer. This for for the aircraft has the same speed. Let's say VC. Now V up here, the air will travel here a shorter distance and travel up there a longer distance. So V bottom, the velocity at the bottom will be less than the velocity at, no, not really. Yeah, yeah. Because the wind has to travel a longer distance, then it means it will travel faster because the time the aeroplane passes through a fixed distance within a mass of air is the same. So therefore, the velocity of air up would be higher. Okay, and through the Bernoulli principle, we know that with the pressure here will have a low pressure here. The pressure will be low here. Sorry, which one? The net effect is that there will be lift. Which one? Okay. Okay, the pressure here will be higher. Sorry. The pressure at the bottom will be higher, but uh, the pressure will be higher here, and the pressure here is low. The net effect is there will be lift, and that principle. So that we know from science, from Bernoulli. This is Bernoulli principle. From Bernoulli, I'm sure you know that already. From Bernoulli, we know that if velocity is low, is low, then pressure is high. Okay, and then velocity is high, then the pressure is low. So that principle we know from science, and the Bernoulli already discovered for us. But now the people, to make sure that it's working here, that now we can create something following that principle, are the engineers. Okay, uh, so I hope that really succinctly puts up across the differences for you. Is there any uh, now people are saying many things on the charts. Okay, so please make sure you, and I need to know that you understand, we understanding each other. Someone type on the chat to show me that we are okay. Yes. Anyone tell me that we understanding each other? The class reps. Okay, okay, so confirm that that's okay. Then the so we talked about the aerospace, chemical engineering, then civil engineering. Now you can imagine and design, you know, um, infrastructure, airports, roads, and so on. And then civil engineers are able to make sure these are realistic, these are reality. Now, there's always a war that goes on, a silent war, so to speak, between architects and engineers, because sometimes in public spaces, for example, architectures want nice large spaces. Okay. Now, in terms of civil engineering, we can only, for example, a beam can only support a fixed span. If be beyond a certain length, then there are other things that you need to make sure the structure is sound. So architects will imagine that they need that space, but it's the engineer who will make sure that that thing is soundly, the space. Just to show you the differences between imagination, and so engineers basically, uh, our job is to make sure what is imagined is actually actualized, and we can say as much for all these infrastructure, dams, buildings, railways, and so on. And then electrical engineers design and say study of various electrical and electronic systems such as circuits, generators, motors, so all the things that you use. I'm sure some of you are using a phone, electrical work of electrical engineers, a magnet work of electrical engineers, generators, motors, even the electrical components of our vehicles. Those are um, um, the work of electrical engineers. Then we have mechanical engineers, the design of physical and mechanical systems. So mechanical systems that move. So we usually say, and for civil engineers, we say we use only 3 equations to design. Okay, equations to design. So in our equations, we say that summation of moments at a point equals 0. Summation of forces at a point equals 0. So let's say vertical, horizontal forces, and summation of vertical forces is 0. And we say that is the domain of civil engineering. Now, when these things are not 0, then we go to mechanical engineering. Civil engineering, we design things that are not moving, like vehicles, No, sorry, not vehicles, like buildings, like you know, things that are stationary. Okay, but of course we can also deal with moving things when although this is a domain of mechanical engineers. We also design together, for example, vehicles. The mechanical components, that is mechanical engineering, but they have to work hand in hand with civil engineers. Planes, okay, the framework and so on. Talk about the trains, talk about the what is it? The ships in the ocean and so on and so on. Okay. Then beyond these four sources vary in the other. I I feel like we have repeated a lot. Naval engineering, mining engineering were major branches. Modern fields sometimes include major branches like aerospace, petroleum system, audio engineering, architectural, biomedical, industrial, material science, and so on. So today we have many, many branches of engineering that we may not mention here, but we mentioned the key. So out of the traditional branches of engineering, civil, electrical, mechanical, we now chemical, aerospace, and now we've we've gone now advanced to mining, the software, computer engineering, and so on, and many of these things, biomedical engineering, nuclear engineering, and so on. The new specialties sometimes combine with traditional fields and form new branches. A new emerging area of application will commonly be defined temporarily as a permutation of subset of existing disciplines. There is often gray area to when given subfield becomes larger and or prominent enough to warrant classification as a new branch. One key indicator of such emergence is when major universities start establishing departments and programs in the new field. For example, these fields there exist considerably overlapped, especially in the areas of application of science to discipline such as physics, chemistry, and mathematics. So basically, what you are pointing out is sometimes is very difficult to distinguish. For example, if you're talking about naval engineering, the navy, okay, these combine aspects, the ship itself combine aspects of civil engineering and mechanical engineering. Mining is traditionally the domain of civil engineering. In fact, if you're studying civil engineering, there are some courses you study which are applicable to mining. So mining tradition. So there is a thin line where now we divorce mining engineering from civil engineering. Nonetheless, for example, in mining, you need the knowledge of the chemical concepts of, for example, refining and getting the mineral. These are aspects that civil engineer may not necessarily specialize in, because civil engineering we are concerned about providing the space, the infrastructure for you to mine safely and get your. But now mining, apart from the fact that you may be required to know all these, the safety and how to extract the material, they may go ahead and establish or specialize on how to define the extraction process and so on. Then aerospace, petroleum systems, audio engineering, those are ordinarily, for example, audio engineering is ordinarily part of not civil, electrical engineering and so on. So the thin line between now, when does it exist on its own? Other things like offshore drilling platform and so on. When you are to extract um, um, oil from the offshore, first you need civil engineers for the structure, the stability to provide the infrastructure. Then the drilling, you may need mechanical engineers through the fluid mechanics and so on. Then you may also need chemical engineers for the part of extraction and so on. Okay, so I don't know if there's a question. I think we finish with that, but we'll go on because Now, some of you are just making comments there. If you have a question, you ask. Yeah? Someone is saying, I'm teaching myself. Make sure that you can't see my screen. What does that mean? It's saying it's sharing. Now I need some notes already with the class rep. Okay. Someone please confirm that you can see my screen, see the notes, and that's the first question I asked. So if you can't see, I don't know, it's check your connection, and you need to be respectful. Otieno says they can see my screen. Someone is saying they can only see me. But the notes are here. I have shared. Is that better? We can't see the notes. Someone is saying they can't see it well. Okay, the notes are with the class rep. I don't know. So I'm sharing again. No, someone has a problem. Even if you see me, in fact, you should see me. If you see me, you are okay. Yeah, if you can see my face, you are okay, and hear me, you're okay. The notes I will share. You don't necessarily need to see the notes, my friend. As long as you're seeing and you're hearing me, that's enough for now. It would be better if you could see the notes, but if for some reason you can't see the notes, you can see me, you are okay. These notes are already with the class rep, okay? I will share again for the benefit of those who are saying they don't have have a lot of time. So that is chapter 2. Chapter 3, I sent the notes, but we are yet to go through it. So I hope we are able to go through it successfully. Now, there was a lot of chaos last time in taking the attendance. You don't need to see the screen. If you can see me, you are okay. Okay, someone is saying is okay. Now, I think there's either fluctuation of internet or something wrong with your connection. Okay. Now, I will share the notes. Now, there was a lot of chaos in taking attendance last time. So, what I will do now is create a link for each class. So, make sure you get the link for each of these class for TLE. So, make sure, and someone is asking which unit this is. Now, this is lack of seriousness. If you don't know which unit is this, you should leave this class. Now, I will share of course, you have to do a card. Someone is asking. I will share the course outline was already shared. Please find out from your class rep. I will share the link for each class. Okay. TLE. Now tell me, I want to see on the chat there which classes are here. TLE, elect ECE, CSC, and which one? MPE, CPE, and what? TLE. I think TLE. The previous class also did not study this course, so please make sure TLE is here. No, not TLE, sorry, which is this? MIT. Okay, so there's EC, there's MPE, there's TLE, there's CSC, okay? And MTI, what is it? MIT, Are you there? So I'll create links for each of these, okay? And then you join the particular one for your class. And then we stop the streaming. Because I think we cannot, for example, the names, the I don't know the university policy about sharing, because these are public platform. We may not share your your details. Okay, so maybe it's not a good thing to share your details. Okay. So at the end of this class, look out for the links for each of those classes and you join the one relevant to you. And then we can take the attendance. Okay. So role of engineers in the society. Engineers apply the science of physics and mathematics to find suitable solutions to problems or to make improvement to status quo. More than ever, engineers are now required to have knowledge of relevant sciences for their design projects. As a result, they may keep on learning new material throughout their career. If multiple options exist, engineers weigh different design choices on the merit and choose the solution that best matches the requirements. The crucial and unique task of engineer is to identify, understand, and interpret the constraints on a design in order to produce successful results. It is usually not enough to build a technically successful product. It must also meet further requirements. So the whatever you marvelous thing you build must satisfy the users. The users must be able to relate with it. Now, to make this point, check some of these ages. The average age here, people born in the average age is 20 what? Please type your. I'm not asking for anyone's age. Just type the average age. These are people that born in 2000, maybe 20, 20. I don't know. Michael Okoth, what is your age? Type. I want to see. Or someone say, okay, 22 is a good. So these are people born in the. So then I think maybe you have seen in 2010, for example, we do not have a lot of the smartphones were already there, but we did not have smartphone. Actually, you don't believe that by 2006, just being able to take a photo and share was something that was marvelous. Is and there was a preserve of celebrities like I think was it either Celine Dion or Mariah Carey was it went to Japan and was able to take a picture and that was a sensation on it. You people may not appreciate it because today you can take your videos, take photos, edit them and add a lot of filters and lie online that you are brown probably and perhaps not so and so casually but if you were in that era, then even being able to take a photo was something that people marveled at. Okay, so you can see there. But my point I want to say, what you are doing, people must relate with it because if you look at the big names like Nokia, okay, there were phones. I know there are still Nokia phones, but do you hear them? I'm yet to see a smartphone for Nokia. Okay, things even if you check now the Samsung, some even have disappeared. LG, some brand names for phones have disappeared. Why? Because they are not able to move on with the times. Okay, so Samsung has done very. I think is it Samsung. There was Motorola also. Motorola, I no longer hear of them. So the ones that who have been, my friend, if you're 31, you should be working. You should not be. I know you're joking, but 31, you are not supposed to be. You should be doing masters or a PhD. You should not be here. Anyway, I know some of you joke. I can see that. But the point is, if those who are not able to move with the times cannot do no longer have sales. Okay, Motorola, someone saying, Samsung, LG, some even have disappeared. Nokia have disappeared because they were not. So I think that makes my point that you should be whatever you're making should resonate with people. Otherwise, you'll face. And this is why I think iPhone has done very well. iPhone is able to to sell because it adjusts and makes sure that the device resonates with the people. And you can imagine you spend nearly 500,000 as on a latest iPhone, but people are still buying it. Okay, so constraints may include in available resources, physical, imaginative, or technical limitations, flexibility for future modifications and additions, and other factors such as requirements for cost, safety, marketability, product durability, serviceability. By understanding the constraints, engineers derive specifications for the limits within a viable object or system may be produced and operated. Then problem solving engineers use their knowledge of science, mathematics, logic, economics, appropriate experience, or tacit knowledge to find suitable solutions to problems. Okay, so many problems in the society we find solutions. You would not imagine how in the before the 1800s. I don't know. Some of you may not know there was a sexually transmitted disease called syphilis and gonorrhea. I think even me in my lifetime, I did not like. How can I say? I did not see the experience, but I read somewhere that when people did not, when penicillin had not been discovered, penicillin is just an antibiotic. People used to the it even affects your brain. You start experiencing dementia, and people died just before because penicillin was discovered. I think in the 1920s, people really died out of. But now you can see now the invent. So that was kind of an engineering. So the science of discovering a keyword, for example. And you see now how that now transformed people's lives through the use of science, penicillin. Now, we also have talked about agrarian revolution. Okay, the we need as a population increased, we we have increased food production and population has greatly increased. These are advantages, of course, we draw from engineering. Okay, then the other thing, you people who are ranting, I can see many of you just joking on the wall. You should be you are happy that you are 20, but you should know in the 1930s, in your 20, you are approaching your sunset days. If you are in your 20s, if now you're 20, but if it were 1930s, you are approaching your sunset days because there were not a lot of medication, there were not a lot of. Well, first of all, you who is saying you're 25, you would already be like an old man. The one saying they're 31 would all nearly dead because you would be like they considered the old man because there was no. Right now, our life expectancy has been improved. People who live, I don't know the average life expectancy in Kenya, maybe 60. Uh, um, 30, if you reach 30, if you are 20 now, those who are 20, you would be having many children. You would be having maybe, I don't know, 10 children, and you'll be nearly old, almost dying. But of course, thanks God to our, invention and so on. a lot of what is it? A lot of immunization and so on. The average life expectancy has more than doubled or tripled, as it were, because of invention. So that's the point we are trying to make. But we should also remember at the back of our minds that as much as with all these innovations, there is a danger. We remember the bomb, the gas that was used to kill people in the genocide by, I forget this name, this German dictator. I'm sure you someone who remembers is was called who? No, not. He was called. Anyone who remembers? Okay, so engineers typically attempt to predict. So again, the other thing we don't like as engineers is we don't like uncertainty. So we try to bring order amongst in uncertainty. We like to predict how things behave and be able to. And this is why you can see even the process of sending a person to the moon took a lot of making prototypes, a lot of tests. You can see what Elon Musk is trying to do. You do a lot of tests so that you're able to get enough data. You're able to predict what would happen. That's the only way we were able to send uh, people to the moon and bring them back. So we don't like uncertainty. We don't like for example, if you are to send people through the spacecraft and you're guessing your way, we like to predict with certainty what is going to happen. And of course, even see the risks and think of mitigation measures. They use, among other things, prototypes, scale models, simulation. So this one, in your study of engineering, you'll do before you do anything in large scale. You do a prototype, you do a test, you simulate. The help of engineers and so on. You do the destructive test and destructive. You do stress test and so on. Testing ensure products will perform as expected. Engineers take on responsibility of producing designs that will perform as well as expected and will not cause unintended harm to the public at large. Engineers typically include factor of safety in the designs to reduce the risk of unexpected failure. However, the greater the safety factor, the less efficient the design may be. The study of failed products is known as forensic engineering. Actually, we even want to know what happens post failure. Actually, we can create a structure just to destroy it to see what is happening. But even because there are things that will happen out of our control, for example, acts of God and so on, even there we do like to do tests and find out what is the explanation or why that happened and can help the product designer in evaluating his or her design in the light of real conditions. The discipline is of the greatest value after a disaster such as bridge collapse, when careful analysis is needed to establish the cause or causes of such failure. So, just some photos to make sure you can relate. So, for example, in space industry, the space. If you are interested in designing spacecraft. So these are simulations showing you the distribution of air flow and so on, and how will that affect um, the how will that affect your the dynamics of your spacecraft motion. Now there is a movie called Hidden Figures on Netflix. You can watch showing just a real story actually showing it's based on a real story. It's not a real story, it's based on a real story showing or reliving how the events that led to the first landing in space. So, as with all modern scientific and technological endeavors, computers and software play an increasingly important role, as well as typical business application. Software, there are a number of computer-aided applications. Um, computer-aided technologies. Specifically for engineering, computers can be used to generate models of fundamental physical processes, which can be solved using numerical methods. One of the most widely used tools in the profession is computer-aided design software, which enables engineers to create 3D models, 2D drawings, and schematic of their designs. CAD, together with digital mockup, DMU, and CAE software such as finite element method or analysis or analytic element method, allows engineers to create models of design that can be analyzed without having to make expensive and time-consuming physical prototypes. These allow products and components to be checked for flaws. So using computers is a good thing because instead of creating, for example, a whole building or a whole spacecraft and you know destroying it, which would be a much more expensive. So you can start to learn certain things by doing simulation in the computer. You can create a model, you can vary it so many ways and see what is happening so that you know many things. So that if you're going to do the test, you do just a few. So instead of doing, for example, 10 models, if, for example, you want to do the effect of shape, okay, then it means in reality you have to make many different shapes, isn't it? But in the computer, you can do many shapes, different and quite a number, without incurring any additional cost other than, for example, the input for the software. I mean, the cost of the software only. But so that in reality, you'd only be able to do maybe one or two tests. But of course, if you are to do this without a computer, it would be more expensive. This allows products, I think I've read say, checked for flaws, assess fit and assembly, study ergonomics to analyze static and dynamic characteristics of such systems, such as stresses, temperature, electromagnetic emission, electrical currents and voltages, digital logic, levels, fluid flows, kinematics, access, and distribution of all information generally organized with the use of product data management software. There are also many tools to support specific engineering tasks such as computer-aided manufacture, software to generate machining instructions, and so on. So if we have complicated or complex machining process, you can, because computer is good at repeatability without making many mistakes, then the once you give that instruction or put that instruction in the computer is very good. It can do it perfectly without making mistakes, as probably opposed to what humans could do. Manufacturing process management software for production engineering, EDA for printed circuit board, and circuit schematics for electronic engineers, MRO applications for maintenance management, and AEC software for civil engineering. In recent years, the use of computer software to aid the development of goods has collectively become known as product life cycle PLM. So what the point here is, computers have become great help because instead of creating prototypes, which involves money and so on, and the number, of course, this does not mean that you will not create prototypes or will not do tests. But the point is the number of tests that you will do will be limited and targeted. So instead of in reality doing 10 tests, just do one. The rest, once you get insights from what you observe, the rest you can do in the computer. And in the computer, you have a lot of leeway. You can change shape. You can do many things without incurring additional cost. Engineering is a subject that ranges from large collaborations to small individual projects. Almost all engineering projects are beholden to some sort of financing agency, company, a set of investors. And so again, as engineers, remember all these things we are doing are expensive, involves money. People want value for their money. You'll have a sponsor, you'll have a client. Okay, so that's the point. So we need to spend the least but get something that is very efficient, so as it were. So we have governments, often the big investors. A few types of engineering that are minimally concerned by such as pro bono engineering and open design. Okay, so if you are, for example, giving pro bono free, those ones have no minimal constraints. Have minimal constants. By its very nature, engineering is bound up with society and human behavior. I've said that. So whatever you design must be satisfying or must fit the needs of the people, the persons. And I usually give this example. I'm sure you've seen this. In some organization, there are parts this way, for example. But you find humans will come and create their parts. I'm sure you've seen something like this. Even at the university, perhaps it happens. So this simple one just demonstrates that the engineering infrastructure in such an instance perhaps does not go hand in hand with the needs of the people. So, but the point here, the engineering um, must is bound by human behavior. So must you know must be able to satisfy the human need or attempt to satisfy the human need. Now, number two, you see there are buildings, buildings. Sometimes you need to provide, for example, ramps and so on. Okay. Then there are certain human behavior. For example, when you're in an upper floor, you want a balcony. So this is the point basically. Every product or construction used by modern society will have influence by engineering design. Engineering design is very powerful tool to make changes to environment, society, and economics. And this application brings with it great responsibility. So again, remember your engineering carries it with itself a responsibility. Now we start now. If the building you are in now if the building you are in now collapses, you can see people can lose lives. So that is the responsibility of about which you speak. Okay, and this can be said of many things. Spacecraft, an aeroplane could kill people and so on. So there is responsibility along and again, remember what we said. The Haber process used to produce a poisonous gas used in the Holocaust. So as much as it's there's fertilizer and so on, people um, develop, produce more food and so on. But there's also the negative side. Okay, so and that's the responsibility of which you speak. Many engineering societies have established codes of practice and code of ethics. So, to prevent some of these things, we have ethics to guide members and inform the public at large. Engineering projects can be subject to controversy. Examples from different engineering disciplines include nuclear weapons, Three Gorges Dam, the design and sport utility vehicles, and so on. So sport utility vehicles can go very high speed, but then the dangers that are involved, use of nuclear weapons, and so on. So a lot of politics around them. Extraction of oil on one hand, we need oil and energy and so on, but then we are destroying the environment. So, okay. The Three Gorges Dam, please read the story. I'm sure you had about the potential benefit to the people, but of course, the displacement of persons. That's the first thing to create space for the dam. Of course, the dam will create a micro environment, with water supply, create electricity, but you're going to displace people. Again, the danger of people downstream if something happens to the dam, you see. So those are, the questions you need to ask. In response, some Western engineering companies have enacted serious corporate and social responsibility. So I'm sure you've had this social corporate responsibility. So because you are extracting from the environment, you need to return something to the environment. Okay. So the organization have corporate social responsibility. Even you are coming to school, you have been probably people contributed money for you from your village. So one day when you become, I don't know, the governor or somewhere, you need to take a few kids back to school, pay their fees as part of your corporate social responsibility. Engineering is a key driver of human development. Sub-Saharan Africa, in particular, has very small engineering capacity, which results in many African nations being unable to produce crucial infrastructure without it. So this is unfortunately true. Um, you can see now, but also I don't know what is happening. You can see now even major infrastructural projects, despite the fact that we teach world-class engineering, this we import too much of you know uh, the engineering staff, the skills and so on. But also, in addition to this, the budget required for engineering is humongous. So sometimes we are unable to raise that kind of budget on our own, unfortunately. The attainment of many Millennium MDG, Millennium Development Goals, require the achievement of sufficient engineering capacity to develop infrastructure and sustainable technological development. All overseas development and relief NGOs make considerable use of engineer supply solutions in disaster and development scenarios. So, was it World Vision? There was is it World Vision? In the villages went, uh, um, building or excavating wells for people, building wells, water wells for people. So, and I'm sure in your village you can hear, you may have heard of some NGOs making such provisions. A number of charitable organizations aim to use engineering directly for good of mankind. So we have Engineers Without Borders, Engineers Against Poverty, Engineers for Sustainable World, Engineers for Change, and so on, Engineers for Disaster. So the point is you also need to contribute after all this engineering we have learned. It's good to be able to contribute to change in the society. Okay, and then so we engineers and other discipline, what is the relationship between engineers and other disciplines? So according to a quote from Carman, scientists study the world as it is, engineers create the world. So like I've said, scientists will get there, will discover the logic, the formula or the reason behind, for example, the famous Isaac Newton. We know now about gravity, why an apple will fall towards the ground. Much more, we talk about Einstein, Albert Einstein, discovered the law of relativity. Is it? Is it? Relativity and so on. So now we understand how the world works. Okay. But now engineers will create in that. Engineers use this principle to be able to make things. For example, knowing the theory of relativity, they're able to send spacecraft from Earth, and because you know that if you were sending it to the moon, you know the movement of the moon, and you know that distance, and you send it in a way that you know at the point the spacecraft reaches or nears the moon will be around. Otherwise, if you do not know, you would send the spacecraft this way, yet at that time, the moon is on the other side, and you can say as much for example, Mars, and and many of these. So there exists an overlap between sciences and engineering. In engineering, one applies science. Both areas of endeavor rely on accurate observation of material and phenomena. Both use mathematics and classification criteria to analyze and communicate observation. Scientists may also have to complete engineering tasks such as designing experimental apparatus or building prototypes. Conversely, in the process of developing technology, engineers sometimes find themselves exploring new phenomena, thus becoming, for the most part, scientists. So sometimes there's a blurry line between engineers and science. Okay, you find most of the people discovered, for example, there's some theorems. You'll hear someone says mathematical scientist or scientist engineer, because there's a blurry line. Okay, in the book Engineers Know and How They Know It, Walter Vicente asserts that engineering research has character different from that of scientific research. First, it often details the areas in which the basic physics and chemistry are well understood, but the problems themselves are too complex to solve in an exact manner. For example, the use of numerical approximation, the Navier-Stokes equation, to describe aerodynamic flow of an aircraft, or the use of Miner's rule to calculate fatigue damage. Second, engineering research employs many semi-empirical methods that are foreign to pure scientific research, one example being the method of parameter variation. So engineering is the next thing we'll talk about. Is engineering is an art and a science, and an art because sometimes you need to go beyond the solid science, beyond the imagination, because there are certain things that in fact science cannot explain, but we know they work. But if we apply science alone, we are unable to. So then that's why we are talking about some empirical. So even then, we know a bit of the science, but we also need to rely on observation. Okay, so even before we know how it works, then we observe and record what we see and try to relate that with the empirical approach. So many things we still don't know how to. As much as we have achieved a lot in terms of development. There are many things we still don't know. We still cannot explain how they work. And we have tried, people have even tried to undo death. Unfortunately, we have not been able to succeed in that. Okay? So, for example, things like death, no one can explain how that works. As stated by Fang et al. In revisions to the classic engineering text Solid Mechanics, engineering is quite different from science. Scientists try to understand the nature, engineers try to make things that do not exist in nature. So engineers will try to imagine the world. Basically, this idea that imagine the world and create it, this is what engineers do. Engineers stress invention. To embody an invention of engineers must put his idea in concrete terms, design something that people can use, people can see, like your phone, the building you sit, you're sitting in a chair, and so on. Okay, and design something that people can use. That's something that be a device, a gadget, a material, a method, computing program, innovative experiment. My point is around you now. I'm sure you can easily identify the handprint of an engineer. A new solution to a problem and improvement to what is existing. So even if you find what is existing is inadequate or cannot serve certain purposes, then you try to make it, adopt it to the current scenario, that becomes an engineering invention. Dimension and characteristic numbers and so on. Almost all engineers working on new designs find that they do not have all the needed information. Now, this is very true. Now, in your study of engineering, you will be told assume this, assume in many things, which in reality you will not be able. You are needed to design, but you don't have that information. Okay. When we teach you engineering, for example, you'll be told assume this value is this, assume that value is that, but it will be unknown. So, but actually, in the field, if you are now to do that, information will not be available, and in which case, from your knowledge of engineering, you decide what that value is. Most often, they are limited by insufficient scientific knowledge. Thus, they study mathematics, physics. This explains why some of you you've studied physics. I think physics, chemistry. I'm not sure if you study biology, and you stay. And in fact, in your study up to fifth year, you do a lot of mathematics and mechanics, because you need that is forms very good foundation for you as an engineer. Often they have to add the sciences relevant to their profession, thus engineering science is born. So out of all these maths, what is happening? So some designs to show you. Although engineering solutions make use of scientific principles, engineers must also take into account safety, efficiency, economy. So it's not just about design, okay? Economy, okay? So that something that that should cost 10,000 is not going to cost 100,000, okay? So that your phone, when you're making a call, the rays, the X-rays do not cause cancer to you. You can use it safely, okay? Of course, you some phones, you try to listen to the person on the other side. You cannot communicate, although maybe that could be a function also of the service provider. So, but my point is basically so that what you're using can do it safely, efficiently, economically, reliability, and of course now for example, for me, I have used an iPhone, so I know it's a very reliable phone. I have had a very bad experience with. Okay, I'm not saying all Androids are bad. Um, probably there are good Androids, but those who, and you'll agree with me, when I say this, many people say I'm arrogant. Um, the Androids have a lot of memory. You install a few things and then you're told memory is full and so on. So for me, I know if I want a good phone, I go for an iPhone. Okay. Then in terms of cars, there are people who say this is a good brand of car. So but that brand of car has. So we're talking about reliability. Okay. Then also certain things like, for example, the ease of the fact that you can get spare parts, because there's no point you can buy something very cheaply, let's say 1,000, but you want to get the spare part. The spare part would cost you 5,000, so it doesn't make sense. Okay. Then there are other things like legal consideration, patent infringement, liability in case of failure, or so if an accident happens, who takes responsibility? Okay. So medicine and biology research showed that Leonardo da Vinci has been described. So some of this is just showing how engineering helps in medicine and human anatomy. Okay, so the human body, there are people who we now have implants, uh, pacemakers. You can have artificial limbs. Okay, you can have artificial heart. Okay, artificial brain. We are yet to get there about artificial brain, but the artificial heart has been, been found to work. Okay, and a lot of research still going on. We have then even that, leave alone that, the fact that we can image something. If something is disturbing you in your chest, we can do an image and be able to see without really opening you up to see what is happening. Okay, we can do CT scan, many things. So those are the process through which now we can do radio X-ray, for example. That is the work of engineering. So we are relating engineering and medicine. So I hope you get that part. Then even the process of making bionics, artificial implants, artificial heart, and so on. Those are works of engineers. Okay. Um, then someone died at the MRI in the USA. They had some chain in their neck, and the magnets in